Why do you think subspaces are important? Can someone tell me why would this be important? Hello? Can someone tell me why subspaces would be important? What do you think a subspace does to the whole vector space? Any idea? Can someone unmute and tell me? Please don't type it in the this one. I wouldn't be able to see it. You can unmute and tell me. So what is the, why would we want to look at subspaces? Why not we be happy with just vector spaces and say, look, all that I want is vector space and vector spaces are there, so I don't have to care about anything else. Yeah? Can someone tell me? So subspaces basically partition the vector space into set of points which belong to the subspace. Okay, so I'll say into set of points set of vectors that are elements of subspace and the set of points which are not elements of the subspace. They are something else. Elements of subspaces or subspace and that set of vectors which are not in the subspace. Okay. Now this is more important. So the first idea about subspaces basically tells you partition, so which are not in subspace. Now we are going to look at something. Okay. What we're going to do is two things we are going to look in the first case. Before we get on to the subspaces, matrices and all, what we do is we'll look at something interesting about the subspaces themselves. How do we construct vector spaces? How do we construct subspaces and all those things? And then we will look at something more. Okay. Now, let's take this. See, in the definition of vector space, we said that if you take, for a set of vectors to be vector space, so let's write this, for V to be a vector space over F, over field with say operators plus and with these two operators, let's consider this field to be real. We said that we need a V to be closed under vector addition. This is what we said, right, yesterday? We said V needs to be closed under addition, vector addition. V should be closed under scalar multiplication. And we said C, V should contain the zero vector. Yeah, we said V should contain the zero vector. Is this okay? Now what we do is we will try to club these two properties together and then say, what does this mean? This means U comma V, elements of V, implies U plus V is an element of V. This means alpha in R, or say field, U in V, U is an element of V. This is what it means. Now, what we're going to do is we are going to club these two and then say, so we're going to say that V is a vector space. I will not say V is a vector space. We'll just look at this. We'll say that the vector W is equal to alpha U plus beta V, where U, V are elements of V and alpha, beta are scalars from the field. Okay, we say that the vector W is a linear combination of U and V. Is a linear combination of the vectors U and V. Is this okay? This is fine. Is everybody getting this? Hello?
Yes, sir, it is fine, fine.
Yeah. Okay. Now, what we're going to do is we are going to look at one more definition. Now, let's take these two vectors. Example, let's take U is equal to 1, 2, and V is equal to 2, 1. W is equal to 1 time 1, 2 plus 1 time 2, 1 is equal to 3, 3 is a linear combination of U and V, where alpha comma beta is equal to 1. Okay, or alpha is equal to beta is equal to 1. Is this okay? So this is linear combination. Now I'm going to make uh, one more definition. What is the definition? We're going to look at what we call as, let's look at this. We're going to talk about linearly independent set of vectors. Linearly independent set of vectors. Now, what do we mean by linearly independent set of vectors? Say, suppose now we take this vector U, which is 1, 2, and vector V, which is 2, 1. Okay. Now, I want to see, the question is, how do we get the 0 vector as a combination of this? How do we get 0, 0 as a linear combination of U and V? Which means, what is it that we want? We want to find out the scalar alpha into 1, 2 plus beta into 2, 1 should give me 0, 0. Now the question is, this means, what are the scalars alpha, beta, such that is the question clear? So what do you think is the scalar alpha and beta? Can you tell me what it is?
0.
What is 0?
Value of alpha and value of beta, if it's 0, then it will give 0, 0.
Any other value that you will get 0, 0? You'll get the 0 vector. So there's one answer. It says alpha is equal to 0, beta is equal to 0, implies 0 into 1, 2 plus 0 into 2, 1, which gives me 0, 0. Yeah, that's brilliant. Any other values? So the question is, are there any other values? Can we find any other values of alpha and beta? Any other value of alpha and beta such that alpha times 1, 2 plus beta times 2, 1 is 0? Hello?
No, sir, is not possible, sir, actually.
Not possible. So we'll write this.
In geometrically that independent.
Exactly. So there exists no other alpha comma beta for which alpha times 1, 2 plus beta times 2, 1 is 0, 0. Is this okay? Such vectors are called as linearly independent vectors. So therefore 1, 2 and 2, 1 are called linearly independent vectors. Now, how do we define them properly? We say that if you have two non-zero vectors, let's take a set of n non-zero vectors. This is very important. A set of n non-zero vectors in a vector space V is said to be linearly independent if and only if and only if well, this n non-zero vectors, we'll take it as say u1, u2, etc., un. If and only if alpha 1 u1 plus alpha 2 u2 plus alpha n un is equal to this is a zero vector. Okay, implies okay, let's say for some arbitrary alpha i's for alpha i's real. Let's say alpha I real. If and only if this equation implies alpha 1, the scalars are all 0. Alpha 1, alpha 2, etc. equal to alpha n. They're all identically 0. Sorry. This is a scalar. This 0 is a scalar. This 0 is a vector. Okay. Example. We already took that. We took that alpha 1 into 1, 2 plus alpha 2 into 2, 1 is equal to 0, 0 implies alpha 1 is equal to 0, alpha 2 is equal to 0. Okay. If that is the case, then the vectors are called linearly independent. Now, what do we mean by linearly independent in terms of geometry? So geometrically, what does linearly independent mean? So what does this mean? Can someone tell me?
Both vectors are different directions.
Brilliant. So if we take this, for example, let's take 1, 2, 2, 1 only. This is say x1 axis. This is say x2 axis. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 5. Okay. Just take this. So what is the first vector? The first vector is 1, 2, which is here. And what is the second vector? The second vector is 2, 1. So that vector is here. So now what is it that we see? These two are in two different directions. So this is 1, 2 vector and this the vector 2, 1. So we say that geometrically, linearly dependent vectors mean these two vectors should be on two different lines. They must be, okay, they are on two different lines if you actually see. So we say that two vectors are linearly independent if they are linearly independent if they are in different direction. Is this clear? If they are in different directions. Now, it also simply means they are on two different lines. So this implies they are on two different lines. Is this okay? Is everybody fine with this? Now what we'll do is, I'm going to ask a question. Suppose I have this. Suppose we have a set. S is equal to 1, 2, and 0, 0. Is the set linearly independent set?
No,
Why?
because that line 1, 2 is also passing through origin and both are diverging to the same point.
So the conclusion that we must say is any set with the zero vector, any set of vectors containing the zero vector containing the zero vector is always a dependent set. Why? Because I want to get a zero vector. What is the well, we'll look at that. It's always a dependent set. Let's see why. Because now I want to look at alpha times 1, 2, alpha 1 times 1, 2 plus alpha 2 times or plus alpha 2 times 0, 0. I must get the zero vector on this side. I can put alpha 1 is equal to 0. That is fantastic. What about alpha 2? If I put alpha 2 is equal to 1, I would still get 0. If I put alpha 2 is equal to minus pi, I would still get 0. If I put alpha 2 is equal to pi power e, I would still get 0 because it is
Anyway,
multiplying the zero vector, right?
yeah.
That means there is no unique way of representing that zero vector. There are infinitely many ways of representing the zero vector, and therefore any set of vectors which contains the zero vector is always a dependent set. Is this clear? Is this okay?
Yes, sir. Yes, sir.
Yeah. Now what we do is we go to the next definition. Next definition, or probably we'll look at something else. So we found that any set of vectors containing the zero vectors always a linearly independent set. Suppose we take this. Suppose we take this set. Suppose S is equal to, let's say, our set 2, 1, 1, 2. Now, what can we say about the linear combination of 2, 1, alpha times 2, 1 plus beta times 1, 2 for different values of R, alpha and beta? What can we say about this? What can we say about this?
That product is non-zero.
For different, yeah, it will be non-zero. But suppose if I take this vector to be, say, B1, B2. For different values of alpha and beta, what would I get for B1 and B2? The question is, are there any two values of alpha and beta, a pair, such that both the pairs will lead to the same B1, B2?
No, sir.
Why is it not happening? Because 2, 1, 1, 2 are linearly independent. What is it that we get? We get for different combinations of alpha and beta, I would get different values of beta, B1 and B2. That means this B vector P. So let's write that for different values of alpha and beta, we get different B vector. That means alpha into 2, 1 plus beta into 1, 2 is always equal to some different B. Is this right?
Yes, sir.
Now, with this linear combination, for infinitely many values of alpha and infinitely many values of beta, how many points can I get? How many B1, B2, how many B vectors I can get? Is the question clear? So we have said alpha is in R, beta is in R, which means we can alpha and beta can ideally take infinitely many values. Now, if I substitute those infinitely many values of alpha and beta in this particular expression, how many different values of B1, B2 I'll get?
Infinitely.
Infinitely many B1, B2. But in that infinitely many B1 and B2, where will it lie? What is the space in which it will lie? Is the question clear? Will I be able to get, okay, the question, I'll refine it further. So the question is, will we be able to get all points in R2? All points in R2 as linear combination of 2, 1 and 1, 2. Can we get this? Will we be able to get this?
Yes, sir.
We will be in a position to get all the points in R2. For the simple reason that suppose if I put this as matrix, yesterday we saw something. What did we say? We said that when we look at the column picture, we told that the first column always gets multiplied by alpha, second column always gets multiplied by beta. Therefore, I will take the set of equations to be 2, 1, 1, 2 into alpha beta is equal to B1, B2. Now this matrix is invertible. Therefore, for every vector B1, B2, we will be able to get alpha beta as A inverse B1, B2. Is this right? That means I have this dabba, which is A inverse, to which I give some B1, B2. Now, the moment I give this B1, B2 as input, this fellow will give me some alpha beta. If I give different B1 and B2, I will get different alpha beta. No two values of the same B1, no two values of B1, B2 will give same values of alpha and beta. Is this clear? And that is precisely what we call as a unique solution to a system of equations. See, after all, these alpha and beta are what? I could have written this as 2x plus y is equal to 3, b1, and x plus 2y is equal to b2. Right? So what does this mean? I can get xy as A inverse times b1, b2. Is that right? That means you give different values of b1, b2, I will get different coefficients x and y. Which means I will get different scalars alpha and beta like what I have here, which are basically my x1, x2 values. Is that clear? Now you see how we have been able to relate what we saw in matrices as invertibility, solving system of equations, boiling down to looking at geometrically as linear combinations of vectors. Is that right? Is this fine?
Yes, sir.
Yes, sir.
Okay. Now, therefore, what we're going to do is we are going to say that, okay, this is what we said. So for different values of B1, B2, we get different alpha, beta. Is this okay? Is this clear? Now let's go ahead. So what we say is this, we'll say instead of the, we'll say all possible linear combinations of 2, 1 and 1, 2 okay, I will not say, I'll put this instead of this, let me write this. Set of all possible linear combinations. Set of all possible linear combinations of 2, 1 and 1, 2 yield the set of all points in R2. Okay. So what we say is, we make a definition now. We make a definition saying, look, therefore, 2, 1, the set 2, 1, 1, 2 is called a basis for R2. Is called a basis for R2. Now, can you tell me what is a basis? How do we define a basis? What is the nature of this set? What can you say about these two vectors?
And linearly independent set.
It's a linearly independent set. And what is it that we get out of this linearly independent set? This linearly independent set, whose linear combinations results in the set of linear combinations that you get, will form a vector space or a subspace. Therefore, this set of linearly independent vectors is basically called as your basis. Is that clear? It is like saying, okay, see, how many colleges are there in Karnataka? Can someone give me number? Some 500 colleges are there, engineering colleges. Hello? Hello? Can someone tell me how many engineering colleges are there in Karnataka?
200.
Okay,
300.
200. Okay, fine. Let us assume that 300 engineering colleges are there. Now, suppose if the VTU Vice Chancellor wants to send a, send a regulation addressing all the faculty members of the affiliated colleges, will he be sending that circular to every faculty in every engineering college, or will he just send it to the principal and then say, okay, you give it off to everybody?
Yeah, it will send it to the principal.
He will basically send it to the principal. So with the assumption that if you give it to the principal, that principal is representing all the faculty members of that particular college, right? And therefore, if you send it to all the 300 principals, let us assume that every college has some 100 faculty members. So it says 300 into 100. If you give only 300 this circular notice to this 300 principals, it will go across to all the 100 faculty members in every college across 300 engineering colleges. Is that right? Is this correct?
Yes, sir. Yes.
Therefore, the set of principals, a principal in one engineering college is not a principal in another engineering college. Is that right? That is also there. Therefore,
Yes,
this set of principles that we see form a basis for the set of engineering college faculty members. If you look at vector space of faculty members, then the set of principles will form the basis for the vector space of faculty members in all engineering colleges. Because if you give the circular to him, everybody in the college is covered. Every faculty in the college is covered. Is that clear? So if you see, why would I say that linear combination of these two fellows, the 2, 1 and 1, 2, will form a basis for R2? It is basically because of this. Suppose if I take alpha times 2, 1. What is alpha times 2, 1? This is basically a line through origin and 2, 1. And the vector 2, 1. Basically, it's a line. Now, the next one is beta times 1, 2. What is this? This is a line through origin and 1, 2. Is this okay? This is a line through origin and it is passing through 1, 2. Now, what does this mean? This simply means I have infinitely many points on this line. I have infinitely many points of this line. Now what I take is I take the linear combination of these two fellows. I will end up getting every point in R2. Is this clear? So 2, 1 is basically like principal of one engineering college. Of, let us say, engineering college 1. Suppose there are only 2 engineering colleges, we assume. This is principal of another engineering colleges, another second engineering college. Now, what is it that we see? We see that alpha times 2, 1 is basically all those professors who are reporting to this principal in that engineering college. The linear combination of 2, 1 is basically the set of all professors who report to this principal of this engineering college 1. Similarly, beta times 1, 2 is nothing but the set of all professors who report to this principal of engineering college 2. Is that clear? Assume that there are only 2 engineering colleges. Now, this is what will happen. So in that case, what do we say? We say that this principal of EC1 and the principal of EC2, that is the engineering college 1 and engineering college 2, basically form a basis for the set of all faculty members across the 2 engineering colleges. Since there are only 2 vectors here, which are basically 2, 1 and 1, 2, which are linearly independent, every other vector is a multiple of one of these 2 vectors on that particular line. And every other vector in R2 is a linear combination of these 2 fellows. So I say that if I have these 2 linearly independent vectors, I can basically reach any destination in R2 through their linear combination. And this is what we call as basis. And we say that the dimension of a vector space or a subspace. I mean, whatever I tell as vector space, it also holds good for subspace. So I'll say a vector space because a subspace is equal to number of vectors in the basis. Is this okay? So what is the basis of this vector space? Whose basis is 2, 1, 1, 2? What is the dimension of this vector space?
2.
The dimension of this vector space is 2, which corresponds to this. Is this okay? Now, let us look at this. What is the dimension of this vector space? Suppose I have a set. What is the dimension of, let's take this. I have a set S, which is nothing but 2x, comma x, where x is real number. What is the dimension of this vector space? This is basically, I'll take x out. This is going to be 2, 1, where x is in R. How many linearly independent vectors are there in this? This set basically contains only this, because every other element would be a multiple of this 2, 1 vector. Is that right? Hello?
Yes, sir.
Yeah. Therefore, this is a one-dimensional subspace, 1D subspace of R2. Now, this is interesting because I know this is a line. This is a line through this entire set is basically a line through origin and 1, 2, the point 2, 1. Yeah, it's a line through the origin and the point 2, 1. Therefore, a line is basically single dimension, R1. We say that. No, x-axis is basically, we don't say it as R1, we say that it is a single dimensional subspace of R2. So now what we see, this is a one-dimensional subspace of R2. Now the question, therefore, what we conclude is, we conclude this. Every vector space slash subspace has a basis. Not just that, it has infinitely many bases. And not just that, the number of elements in every basis is the same. is the same for a given vector space. For a given vector space slash vector subspace. Is this okay?
Yes,
Yeah.
sir.
Now let's take an example. We already saw 2, 1, 1, 2 is a basis for R2. Can someone tell me any other basis for R2? 1, 0, 0, 1 is another basis for R2. Is that right? Pi root 2 E minus 5 basis for R2. 1, 0, 1, 1 basis for R2. So you can find infinitely many number of for this. Out of all these things, this fellow is called standard basis, because every point in R2, say x comma y, can be expressed as x into 1, 0 plus y into 0, 1. Therefore, 1, 0, 0, 1 form the standard basis or trivial basis. Is this okay? Is this fine? Shall we go ahead?
Yes, sir.
Now I have a question. What is the question? So what is the definition of basis that we said? Basis is nothing but set. Oh, we haven't written that. Okay. Basis is nothing but, let's write the definition. Basis, a set S of linearly independent vectors whose linear combinations span an entire vector space or subspace, vector space or subspace is called a basis for the vector space or subspace. Is this clear? Now I'm going to ask a question. What is the question? Recall that this is a vector space. Is that right?
Yes, sir. Yes, sir.
What is the basis for this? For this vector space? Because we just said a few minutes back, every vector space or a subspace, we made that. No? Every vector space or a subspace has a basis. In fact, it has infinitely many bases. And every basis is a set of linearly independent vectors. That definition also we have given. Now, this vector space just contains the zero vector. Now, what is the basis for this?
Itself,
Hmm?
the same vector space itself is the basis.
Oh, that cannot be the basis. A vector space cannot be basis.
No,
Set of vectors can be basis.
yeah, 0, 0 itself is the basis.
Aha, now we are caught because I am leading you properly to, they say no. I'm leading you properly to ditch. What is that? Because I have already made this statement. I cannot escape from this. I said any set of vectors that contains zero vectors is a dependent set. right? That definition, this statement also I have only made. This statement also we have made. What is that? We have said that every vector space has a basis, infinitely many bases. And then we have said a basis is a set of linearly independent vectors. Now I've put everybody in soup asking for a basis for this vector space. Yes? What do we do with this? So can you give an exemption to this saying, look, no. This fellow is, though it is a vector space, it does not have a basis. That means our entire theory will go wrong. If we say that this is a vector space which does not have a basis, our theory that every vector space has a basis goes wrong. Suppose if we tell you that this is not a vector space, then there is something seriously wrong, because we have to give some kind of a special place for that zero vector itself. Because we already know, if you in the zero vector, in the set containing the zero vector, you add two zero vectors, you will get zero vector. The zero vector is already there. You take multiple of zero vector, it will still be a zero vector. Therefore, it naturally falls into that vector space definition. Therefore, that will be a vector space. What do we do now? Is the question clear to everybody? Is the confusion clear now? First of all, let us get the confusion clear, then we'll get a clarity, we'll clarify the confusion. Is this clear?
Yes, sir.
This zero vector has put all our definitions into some kind of a contradiction now. So what is the basis for this vector space?
Can we have 1, 0 as a basis?
Because that vector is not even there. How can you put 1, 0 there? Both the components are 0. You cannot put 1, 0 here. If you put 1, 0 as the basis, it will correspond to the x-axis. It will not correspond to the origin. Because any point on x-axis is going to be multiple of 1, 0. Is that right?
Yes, sir. Yes, sir.
We are doomed now. Everything is fallen flat. Right? Don't worry. Life is that easy only. It's not that complicated. It gets complicated only when we think complicated. So what we do is we'll make life easy. We will say, by definition. So when we say by definition, nobody should ask us a question. Why this is like this? So we'll say, by definition, the basis for this vector space, any vector space which contains just the zero vector, n component zero vector, 2 component zero vector, 100 component zero vector, whatever that is the empty set. Is this clear? So what we are going to say, the basis, it is like one axiom where we say probability of the sample space is 1, right? So now here we say, by definition, the basis for the zero vector space is the empty set. Is this clear?
Yes, sir.
Yeah. So now we have got all our points right. Everything is set. So even for the zero vector space, now I'm getting a empty set. No, but I have a question. What is the question now? I have to look at dimension of this vector space. So what is the dimension of this vector space? Dimension of this vector space.
Zero, zero.
Why zero?
No one pivot or that's empty set.
Because it is empty set. Because empty set is a linearly independent set, and it is there's nothing out there. The dimension of the zero vector space is 0. Is this clear? This is a very, very important takeaway for us. This is a very important result for us, because we're going to do something in terms of matrices, and then we're going to get this always. Is this clear? So the zero vector space has a basis which is an empty set, and the dimension of the zero vector space is always 0. Is this okay? Is everybody fine with this? Shall we go ahead?
Yes, sir.
Okay. Now I'm going to ask you some questions. Let us see if all of us are able to get this. What are the questions that I'm going to ask you? I have to think. Okay, let's look at this. Consider the following. What do we consider? Let's take this. 2x1 plus x2 is equal to 0. 2x1 plus 4x2 is equal to 0. Okay. This system of equations that I have, I'm going to call this as homogeneous system of equations. Okay. I'm going to call this as homogeneous system of equation. A system of equation where in which the right hand side is 0, I'm going to call that as a homogeneous system of equations. That means I'm going to have AX is equal to 0. This is called as homogeneous system of equations. We will have to see why it is called homogeneous system of equations. We'll come back to it in a minute. Now I want you to solve this. Can you please tell me the value of x1 and x2?
0, 0. Sir.
That's brilliant. So x1, okay. x1 is equal to 0, x2 is equal to 0. It's a solution to this. Yeah? Do we have any other solution to this?
No,
Are
sir.
there any?
No, sir.
No other solution to this, right? Now, I'm going to look at another problem. I'm going to retain the same thing. I'm going to look at this. 2x1 plus x2 is equal to 0. I'm going to say 4x1 plus 2x2 is equal to 0. Now, I want to find out the solutions to this, to the above. Example 2.
We will get many solutions.
We will get
Many
first of all-
solutions.
Okay, so we get many solutions. Now, let's look at this. Many solutions. I want to see the set of all solutions to this. I want to look at the set of all solutions. That means I want to look at set of all x is equal to x1, x2 such that ax is equal to 0, that is such that 2, 4, 1, 2 into x1, x2 is equal to 0. Okay. Now, question 1 I'm going to ask is this. Question 1. I am going to give a name or I'm going to give a notation for this. I'm going to call this as NA. I don't even know, but I'm just trying to give a notation called NA for this. So my question is, does NA contain x1, x2 is equal to 0, 0? That means, what does this mean? This simply means is x1 is equal to x2 is equal to 0 a solution to x equal to 0.
Yes, sir.
It is always a solution to 0, this ax equal to 0, which means ax equal to 0 is a consistent system, which means it always contains a solution. What is its solution? X equal to 0 is always a solution. So the answer is yes. So NA contains the 0 vector. Contains, we'll say 0, 0. Now what I'm going to do is the second question. Can you give me two different solutions for this? You said infinitely many. Can you at least give me two of these solutions for this system of equation? Say call them as u is equal to u1, u2. Can you give me some number for this u1, u2? And v is equal to v1, v2. Can you please give me some number for this?
1 minus 2.
1 minus 2. That's brilliant. So u is equal to 1 minus 2 is a solution. Can you give me something for v?
2 minus 4. We can go in multiples, sir. Many solutions will be there.
Okay, 2 minus 4. We'll take that. Now I want to check whether u plus v, that is 1 minus 2 plus 2 minus 4, is u plus v a solution to a equal to 0, ax equal to 0. I want to look at this. What is this? 1 minus 2, 1 1 minus 2 plus 2 minus 4. What is u plus v? U plus v is 1 plus 2 minus 2 minus 4. So which is
3 minus 6.
3 minus 6. Is 3 minus 6 a solution to this?
Yes, sir.
Yes, yes.
Yes, sir.
A solution? Yeah, it is indeed. That means, this simply means this 3 minus 6 is also an element of Na. Is that correct? Or how did we say Na? Na is nothing but set of all solutions to x equal to 0. Right? Now we see it already contains 0 vector. Fine, we have taken it. Then what we said, we found two vectors which are solutions to the system of equations. Two solutions to the system of equations, namely 1 minus 2 and 2 minus 4. And then what we did, we took the linear combination of these two, and then we said that the linear combination is also a solution to x equal to 0. That means this u plus v is also an element in Na. Is that right? That's what we have to conclude. Is that correct?
Yes, sir.
Now, if you add two vectors and the resultant is also in the same set, what do you call that as? What do you call that set as?
Closed under addition.
Exactly. Therefore, we say that Na is closed under vector addition. This is interesting. Now, it is giving us some hope. What is the hope? Look, this Na contains 0 vector. It is closed under vector addition. Probably, if it is closed under scalar multiplication, then we can call Na itself to be a vector space, or worst case, we can call it to be a subspace. Is that right?
Yes, sir.
Yeah. So we always have some hope. No, we see that, okay, we are trying to, let's assume that we are going for interview. We want to look whether our luck works or not. What do we do? First of all, we see, when we start, we see someone who is very close to us, who had been lucky in the past, coming in front of us. We say, okay, fine. First step is clear. Therefore, maybe there's a chance. Now I am putting second condition. If this bus number comes opposite to me, maybe I will definitely get, okay, fine, because this has happened in the past. I see that bus. Now what do? I hope the third condition also satisfies so that I get my job. The interview is clear. This is all kind of some, we have this, interesting beliefs and our own sense of things, no? So now I want to look whether if Na is closed under scalar multiplication. Now the question is, the third point that we're going to look at is, let's take this. Question 3. Now consider u is equal to 1 minus 2. Yeah, 1 minus 2 or minus 2, 1. 1 minus 2. Now take alpha is equal to 23. Now what is alpha u? Alpha u is 23 times 1 minus 2. Now what do we get? 23 minus 46. Is this a solution to x equal to 0? Is this a solution to x equal to 0? Is 23 minus 46 a solution to x equal to 0? Can you please check the equations and then tell me? If you substitute x equal to 23 and x2 is equal to minus 46.
Yeah, it is a solution, sir.
Ah, that's interesting. That makes, the answer is yes. Now, what does that mean? This means even alpha u is an element of Na. Right? Na contains the 0 vector, is closed under vector addition, it's closed under scalar multiplication. So what can we tell about Na? What is that set of vectors which is closed under addition and scalar multiplication?
It is closed under scalar multiplicative.
It is closed under scalar multiplication. We have already proved that it is closed under scalar vector addition. We have proved that it contains 0 vector. Therefore, any set
Is a vector space. Vector space.
exactly. Brilliant. So we say Na is a vector space. Now, there is a name for this. This Na is called null space of A. Okay. Na is the null space associated with the matrix A. Is this clear? Na is the null space associated with the matrix A. Therefore, now I have a question to ask. What is the question that I want to ask? Okay, let's look at. So we have just looked at the set of solutions to the homogeneous system of equations. That is all we have done. So this is basically now. What is the? I mean, how is this? Can you tell me what is the null space of A for this particular A? This is the set of points which are on the line 1 minus 2. Is that right? X real. Is this right? That's what we said, no? 1 minus 2, 2 minus 4, 3 minus 6, 23 minus 46. Any multiple of this 1 minus 2 will be a solution to Ax equals 0. Is that right?
Yes, sir.
Yes, sir.
Now the question is, what is the geometry of Na?
Line passing through the origin
And it is a line through origin
and the point 1 comma minus 2.
and 1 minus 2. See, we have looked at all the points in R2, but we only found that the solution to Ax equal to 0 lies on this line passing through origin and 1 minus 2. Is that right? What is that? Therefore, this is not all the points in R2, but a subset of points in R2. Is that right?
Yes, sir.
Yes, sir.
Therefore, what we call NAS. Therefore,
Basis.
no,
Yeah,
Na.
subspace of R2.
Subspace.
That's brilliant. That's brilliant. Na is a subspace of R2. Na is not a full-fledged vector space like R2, but it is a subspace in R2. Is this clear? Associated with A. That is more important. Okay. So in fact, I will write this. Na is a one-dimensional subspace of R2 associated with A. Is this fine?
Yes, sir.
Yeah. Now, I have a question. In this case, it is a one-dimensional subspace associated with A. Let us go to this example. The first example that we took. What is that? This example. Can you tell me what is the null space of A in this case? Null space of this A.
Origin.
Na is nothing but origin.
Origin.
So what is the dimension of Na in this case?
0.
It is a zero-dimensional subspace of R2. It's a zero-dimensional subspace of R2 associated with A. With this A. Okay. Is this fine?
Yes,
Now,
sir.
basically, what has A done? The matrix A, if you want to do Ax equal to 0, what has A basically done? I'm only looking at symmetric, I mean, not symmetric matrices. I'm just looking at square matrices. The rectangular matrices, we will just take it up in a few minutes. If I take square matrices, what has this null space done? The set of solutions to, suppose if I take Ax equal to B, suppose I take Ax equal to B, what has this, if I look at Ax equal to 0 and I look at the solutions to Ax equal to 0. What does the solution to Ax equal to 0 mean? Set of solutions, let's put. That means null space of A. What has it done to entire R2? See, we take this. We take this. This is x1. This is x2. And this entire space is R2. Is that right? Now, what is the solution to this system of equation? What was the question that I had? I had the question as 2x1 plus x2 is equal to 0. So we had this 2x1 plus x2 is equal to 0. 4x1 plus 2x2 is equal to 0. This is the equation that we had. And we were looking at the solution to this. What has it basically done? So this is 1, 2, 3. This is minus 1, minus 2. This is 1, 2, 3. This is minus 1, minus 2, minus 3. What we want? We want 1, minus 2. 1, minus 2 point here. 2, minus 4. 1, 2, 3, 4. 2 minus 4 is basically a point here. 0, 0 is already there. Then I have minus 1, minus 1, 2. Let's assume that it is somewhere here. minus 1, 2 is here, and oh, sorry, minus 1, 2 is here, and minus 2, 4 somewhere here. Okay, minus 1, 2, minus 1, 2 is here. Sorry. And minus 2, 4 is a point somewhere here. Minus 2, 4 is a point here. Now let us look at what is happening to this. They basically do this. Is this clear to everybody? Assume that this is 0, 0. Like how our students do. If it doesn't go through the point, we make the point bigger such that it goes. Right? Now, what has this null space of A done? Null space of A basically has done this to R2. It says, look, I have one subspace, which is basically the set of all those points which are solution to this. All the rest of the points which are not in this line, I don't really care. They don't even form a subspace. Why would they not form a subspace? Any idea? See, I have null space, which is a subspace in R2. Is this right? If you leave out this set of points in null space of A and look at all the other points, it wouldn't form a subspace. Can you tell me why?
0, 0 is not there.
That's brilliant, because it's basically complement of NA, therefore 0, 0 is not there, it wouldn't form a subspace. Therefore, your null space of A is like that cake. I mean, it's like that knife. What it has done? It has basically cut our R2 as to 1 as your matrix A. You will say this, if the matrix A has basically cut R2 into 2 parts, it's like that knife which you used to cut. One part is a subspace and another part is not a subspace. What is that subspace that we have here? That subspace that we have here is NA. Is this clear? Is everybody clear? Shall we go ahead?
Yes, sir.
Yeah, now we haven't answered one question. What is this question? We said it is homogeneous system. What do we mean by homogeneous system? We said AX equal to 0. But why should it be called a homogeneous system?
Single variable.
But if a single variable.
Trivial solution.
There is no trivial solution. You have non-trivial solutions also here, no? We took 1 minus 2, 2 minus 4, 3 minus 6 and all to be non-trivial solution. So why do we call AX equal to 0 to be a homogeneous solution? Homogeneous system rather. See, we will look at this. In chemistry, we have heard about homogeneous mixture. Have you heard about this? Long time back in chemistry. You put salt and sugar in water and mix. They mix seamlessly, whereas if you try to mix oil and water, they won't mix. You put milk and water, they will mix. You put again oil and water, they don't mix, right? Which means once they have mixed, you cannot get them back. Is that right? That's what you call as a homogeneous solution or a mixture in chemistry. Right? Now, let us consider this case 2, 1, 4 minus 2 into x1, x2, which is 0, 0. Now, I put this 0, 0 here. So I know the output is 0, 0. I put 1 minus 2 here. 4, 2. Yeah. I put 1 minus 2 here. I get 0, 0. I put 2 minus 4. Oh, I still get 0, 0. I put 0.5 and minus 1. I still get 0, 0. Now I tell you, look, take this dabba A. Let's take it as A inverse. I don't even know what is happening. Suppose if I give 0, 0 as the input to this. Find out that x which gave me the 0, 0. Will it work? Is it possible for us to find out one particular solution x such that AX equal to 0? Is the question clear to everybody?
Yes, sir.
Now, can you give me the answer?
That again it will give the answer, point like 1 comma minus 2 only, or
It won't
this
give.
combination 2 minus 4.
But I want to specifically know which one. See, 2 minus 4, in all certainty, it is different from 1 minus 2. Except that it is a, see, if you say it is like this, then if you go to a company for work, somebody tells you, look, since 20,000, let's say 60,000 salary and 30,000 salary are multiples of each other, I will give you 30,000. Why 60,000 rupees? They can always say that, no? Entity wise, 30,000 and 60,000 are different. Entity wise, 1 minus 2 and 2 minus 4 are different. Is that right?
Yes, sir.
Therefore, even if it gives me 2 minus 4, I have no information regarding whether I gave 1 minus 2. Right? That means all these numbers, they form some kind of a mixture such that when you try to figure out giving 0, 0 as the input and trying to figure out what is the output and what was the original input that I had given to get a 0, 0, it is impossible for me to nail which was the input that I gave. So that is what is called as your homogeneous system. Best, have you learned logic gates? I mean, I don't know, what is the audience group comprising of? Is it maths teachers or it is across departments and this one?
All the department together, sir.
So have you done logic gates at some point of time? OR gate,
Yes, yes.
NOR gate. People have done this. Now, I'll give you a simple example. Suppose let's take this AND gate, where I give X comma Y as input and take Z as the output. Oh, yesterday we saw this. We don't even have to look at the OR gate. We took this binary field, right? We took this 0, 1. Okay, sorry. In yesterday's class, let's see if I can pull that out. Vector spaces, we did fields and all, right? Yeah. Is that? Yeah. This is what we did yesterday. You remember when we did multiplication, we said that you take these two elements 0, 1. Just 1 minute. We said that take these two elements 0, 1 and you do multiplication. Now, if I take multiplication of 0 and 0, I get a 0. If I take the multiplication of 0 or 1, I still get, this is 0. These two multiplied together, I get a 0. These two multiplied, I get a 0. This and this multiplied, I get a 0. Right? Now the question is, I tell you that the product of the two inputs that I have taken is 0. X into Y is equal to 0. Now I tell you, find X and Y. Can we say anything about this? Let's like this.
Anyone is 0.
Exactly. This is X, Y, Z. This is 0, 0, 0, 1. We'll take this as 0, 0, 0, 1, 1, 0, 1, 1. Now, if I tell you that the output is 0. Find out my input. What is it that I can tell? All that I can tell is one of the inputs is 0. It does not clearly tell me which of the inputs is 0. Is that right? I still have certain uncertainty. This is like that homogeneous system. Is this okay? Is this okay? Shall we go?
Yes, sir.
Let's go ahead. Let's go ahead now. Okay. So are we able to understand this idea of homogeneous system? Now, in addition to this null space, now what I'm going to do is, the moment I say A has a null space associated with this, null space NA, which is a subspace. Now, I want to look at A transpose and see whether it has a null space. A transpose also has a null space, which I call it as null space of A transpose, which is a subspace. Is that okay? A transpose also has. So what I'm going to tell is, there are two null spaces associated. Null spaces associated with A. What is that? One which is, as a result, the set of solution to Ax equal to 0. And the other one is, say, some A transpose Y is equal to 0. I want to look at this Y. So This I call it as the right null space when I look at the AX. A into X is equal to 0, where I'm going to look at all that X. I'm going to call that as a right null space. And the other one, A transpose Y, this is basically the null space of A transpose. This I'm going to call it as left null space of A. Okay. So there are two null spaces associated with the matrix A. Now I'm going to look at one more. What we did, we put the right hand side 0, and I want to look at the solution to AX equal to 0. Instead of that, now I want to look at right hand side. So what I want to do is I want to look at this. Look at all B is equal to B1, B2, which can be expressed as AX. Is this clear? Is the question clear?
Yes,
If
sir.
I want, I'm only going to, why is this very, very important for me? For example, let us look at this. Suppose, what does this basically mean? If I take a function f of x is equal, y is equal to f of x, what do I call the set of values that f of x can take? This is basically the domain. Is that right? And what about y? That's basically range of this function. Is that right? Is this correct?
Yes, sir.
Yeah. Now, suppose I give you this. Let us take x to be set of all integers, positive, negative, both positive and negative, ranging from minus infinity to infinity, all integers, okay? And I want to look at this, f of x is equal to x squared. Now, can you tell me the domain of this and the range of this?
So range is all or positive.
Range is all values positive, right? Range is basically, I'll put set of all n's which are greater than or equal to 0. Domain is
Both negative and
It can be
positive.
negative or
minus infinity, less than or equal to n, less than or equal to infinity. And n is integer. Is this right? I'll put it this way. That means even for a function like x squared, I'm not covering, if I take the entire set of integers positive and negative together, my range is only limited in the sense it is only on the right hand side. Is that right? And what is it? Am I going to get all the numbers here? Can you please tell me? What is the range? N is greater than or equal to 0 is fine, but what is the number set of numbers I'm going to get? If I put the numbers that I'm going to get are only this 1, 4, 9, 16, 25,
all square
30,
term.
all the square term. That means it is a subset of the set of integers. Is this clear? Is this clear?
Yes, sir. Yes, sir.
Now, that means I am going to look at only those n which can be expressed as x squared. Is this right? This is nothing but set of n such that it is equal to x squared. Is this correct? The same way what I'm going to do is, I'm going to look at ax equal to b, but what I'm going to look at is, I'm going to look at set of b's which can be expressed as ax. Is this okay? Now let us take the first example that we took today. What is the first example that we took? First example that we took was 2x1 plus x2 is equal to 0. Instead of 0, I will now put b1. And we said 4x1 or 2x1 plus 4x2 is equal to b2. I'll put 2x1, 4x2 is equal to b2. Now, I want to write this the column way. So I'll write this as x1 into 2, 2 plus x2 into 1, 4 is equal to b1, b2. That means, what does it say? b1, b2 is the linear combination of 2, 2 and 1, 4. Is that right? Is this right?
Yes, sir.
Yeah.
Yes, sir.
Now, what are all the b1s and b2s that I can get here? What can I say about these two vectors in the first place? Do we say something about these two vectors?
Independent vectors.
Linearly
Exactly. These two are
linearly.
linearly independent vectors. The moment I have two linearly independent vectors, what is the set of B1, B2 that I can get? Entire R2 I can get. Is it right? I can get entire R2, right? So what does it mean? It means every vector in R2 can be expressed as x1 into 2, 2 plus x2 into 1, 4. Now, what did we say about R2? Is R2 a vector space?
Yes, sir.
R2 is also a subspace, right? Basically, now what we're going to do is we're going to say this. We're going to say the set of all D vectors, B is equal to B1, B2, which can be expressed as AX, be expressed as AX, that is linear combination of columns of A. We are going to call this as, it's called the column space of A. Column space of A. It is also called as range space of A. This is a vector subspace. Is this okay? Is everybody clear with this? Is everybody fine with this? Can we go ahead?
Yes, sir.
Now I'm going to ask another question. Let us take the second example. What was the second example that we took? The second example that we took was 2x1 plus x2 is equal to 0. 4x1 plus 2x2 is equal to 0. This is what we took, right? This is what we took. Now, I will put instead of 0, I will take B1, B2. Can you tell me what is B1, B2, the set of all B1, B2s? Can you tell me this?
So infinitely many solutions.
No, I want to know the set of B1, B2, which can be written as, so I will write this. I want to know what is the set of B1, B2, which can be written as x1 into 2, 4
Yeah.
plus x2 into 1, 2.
But both dependent vectors. So 2, 4, and 1, 2 dependent.
Exactly.
It is a
So,
dependent vector.
Exactly. So let us write this. This is nothing but x1 into 2 into 2, 1, 2, 1, 2
Yeah.
plus I will take this as x2 into 1, 2. Is this right?
Yes.
Yes, sir.
Which means I will write this as 2x1 into 1, 2 plus x2 into 1, 2. Can I do this?
Yes.
Which means I can write this as 2x1 plus x2 into 1, 2. Can I do this?
Yes.
Which means I can write this as, say, some constant times k into 1, 2. For different values of x1 and x2, this will change. Which means now my b1, b2 is basically a multiple of 1, 2. That's all. It's a multiple of 1, 2. So this is nothing but multiple of 1, 2. Is that right?
Yes.
Therefore, now if I take multiple of 1, 2, what is the geometry of this? Can you please mute your...
AX.
Yeah, can you please tell me what is the geometry of this?
Line passing
Overlap.
through the origin.
Passing through origin.
Overlap that. Both are same line.
No, it's basically a line through origin. This, I'm asking about this square, this one. Line through origin and through 1, 2. No, we already know line through origin and 1, 2 is what? It's a subspace of R2. Is that right? We know that it's a
Yes, sir.
subspace of R2. And therefore, what are we looking at? We are looking at the set of B's which can be written as AX. And therefore, this also becomes a subspace. Is that right? So, Now what I'm going to do is I'm going to say the range of A is equal to 2412 is a one-dimensional subspace of R2, right? And we say column space or range of column space of A, or probably we'll say range of and is given by x times 1, 2, where x is the real number. Is everybody getting this? Is everybody
Yes,
getting
sir.
this?
Yes, yes, yes.
Okay, now I have, therefore, what is the basis of range of A? 1, 2 is the basis of range of A. What is the basis for null space of A in this case, in this particular example? 1 minus 2 was the basis, right? This was the basis, right? Basis for A. We wrote it here, right? X into 1 minus 2 is the geometry of null space of A, is a line through 0, 0 and 1 minus 2. So the basis is 1 minus 2. Is that right? Now, what is the dimension of null space of A? Since there's only one vector, we have already called this as a one-dimension null space. So this is null space is one dimension. What about the range? For the same matrix, what is the dimension of the range? What is the dimension of the range? That also we said it is a line through origin. It's a one-dimensional subspace. So this is also 1. Yeah. Now we have a name for these two. What are the names that I'm going to write? Let's take this. The range, the dimension of null space of A is what we call as nullity of A. I will generalize this to rectangular matrices in the afternoon, and then we'll take up eigenvalue, eigenvectors and stuff. And the dimension of range of A, we call that as rank of A. Now you see the rank of a matrix basically comes into picture through the dimension of the range. This rank and what you call as matrix ranks are the same. Is this clear? So this is what we call as rank of A. Okay. Now, therefore, what we see is, similarly, we said that if you have A and null space of A, you have something called as null space of A transpose. Similarly, if you have range of A, you also have a range of A transpose. So what we say is, there are 4 fundamental subspaces associated with a matrix A. A matrix A, they are A, they are null space of A. There's a name for this. It is also called as kernel of A. Then we have null space of A transpose. Then we have range of A or column space of A. Then we have range of A transpose, which is range of A transpose, which is also the column space of A transpose. Since the columns of A transpose is nothing but row of A, this is also called as row space of A. The columns of A transpose is nothing but rows of A, right? So this is row space of A. And this one is called left null space of A. So what we do is, in the afternoon, we will see where are these spaces located, subspaces located if I take a matrix A, M cross N, rectangular matrix. And once we have this idea, what I'll do is, we'll straight away go into eigenvalue, eigenvectors, and then little bit on orthogonality. Then we'll do singular value decomposition. PCA, I will do when I do my covariance matrices. So I will take you till SVD and stop there in today's class. And when we do statistics, because I want to get to the idea of covariance and all those things. So when I do covariance matrix, I will talk about PCA. Okay. Are there any questions?
No, sir.
Everything is
Any
fine?
book for this?
Huh? Hello?
Hello.
Yeah, yeah. I think there is some background noise. Yeah.
Hello.
Can you please? Yeah, yeah. Please go ahead.
Actually, any book, a textbook, so that we can just go through it again.
Yeah, definitely. I'll suggest some textbooks. You could probably note them down. Of course,
Yeah.
Gilbert Stan's textbook is very good. That's like Bible of this one. So you'll have Introduction to Linear Algebra. The latest 5th edition book is too good. 4th, 5th, any edition, anything is fine. Introduction to
Okay.
Linear Algebra by Gilbert Stan. But there are quite a few other books. I'll just give an idea about them. These are even more interesting. There is a book by on linear algebra, applied and pure algebra,
Okay.
applied and pure. I'll just give you just a minute. Applied and pure by Edgar Goodair. This is a fantastic book. If you want to see visualizations, if you want to look at all kind of geometry and all those stuff, I would suggest that you look at Practical Linear Algebra. By Farron and Hansford. These are pretty interesting books. I mean, you will not feel tired of reading these books because the way they present concepts is like quite amazing.
Okay, sir. Thank you. So,
Okay.
we at least once we practice on more, then it would be more familiar with all the terms.
Yeah, definitely, definitely. Now that we have learned the concepts, it's always nice to go back to textbook and then figure out if we are able to relate to the concepts that we have learned here with the concepts which are given in the textbook and look at examples and stuff. Okay.
Yes, sir. Thank you.
Yeah. Thank you. Any other questions? Any queries? So is it like, when are we going for lunch? Okay. Sir, can we wind up now? Yeah, go ahead.
Thank you, sir.
We'll wind up and we'll meet at 3 o'clock. Yeah.
Yes, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thanks a lot. Thank you. Yeah. Thank you.
Thank you all. So we shall meet at 3 in the afternoon. Thank you.